Have you got sound playing, mate, or are you talking to this?
All of this was done through the use of spherical surface area formulas of common knowledge. However, just how the formulas are derived and developed is often overlooked. One would assume that the discovery of these equations would have come from the modern era. It was the ancient Greeks and Phoenician mariners who used the theories of spherical geometry to navigate the waters of the ancient world. It was in fact Claudius Ptolemy who was the first to suggest that the Earth was in fact not flat, yet round and spherical. Ptolemy went on to create the Ptolemaic system, his version of what he thought the solar system looked like. All of this was done through the use of spherical geometry. Numerous mathematicians from ancient times contributed to both the volume and surface area formulas. It is obvious to assume that the foundations laid by the early mathematicians have augmented our ability to comprehend modern problems using somewhat ancient solutions. The volume of a sphere is very interesting, as people knew how to find it after a discovery from Archimedes. Yet, there was no knowledge about irrational numbers and pi. Consider a sphere with radius r and a shaded disk bounded by the sphere with radius x. To find the volume of the sphere, we would use Pythagoras' theorem to find the area of the shaded disk. We would then integrate the area of the shaded disk in respect to z. Take note on the use of integration. Surface area of a sphere. Similar to the volume of a sphere, numerous conditions contributed to theories and equations in regard to the sphere's surface area. 1,800 years prior to the discovery of calculus, Archimedes used Cavalieri's principle to show that the surface area of a sphere is 4 pi r cubed. We now move on to the equation of surface area of the sphere to prove that the surface area of the sphere is 4 pi r squared. We first need to know the arc length of the line in the integral form. For the equation of semicircles, the integral is to integrate from b to a of square root dx squared plus dy squared. Then we can get the formula of the surface area of the sphere by rotating about x-axis, which gives the formula E equals to 2 pi integration of y root dy by dt whole square plus dx by dt whole square from A to B. The circle is then parameterized, which ends up giving the equation A equals to 2 pi integration of r sine t root r sine t whole square plus r cos t whole square from 0 to pi. Hence, solving this equation will prove our statement. Similar to the ideology used above in regard to integrating, say we have a sphere similar to that of a babushka doll with radius r. There are infinitely many spheres inside a main sphere. If we wanted to find the volume of such a sphere, we could sum the surface areas of all the spheres inside the main outer sphere, which is essentially integration. It is through this notion that the derivative of the volume of a sphere would return the surface area of a sphere. When we derive and integrate, we tend to see an order in regard to dimensions and geometric functions. On to the question of whether the relation holds for higher dimensions, we look at following formulas. It's important to consider that E equals number of dimensions in these formulas. So we have the surface area and the volume. It is also important to consider that these are unit pairs and don't show the radius of r, so r grows as r to the power of p. Likewise, if the dimension was equal to 4, it would be r to the power 4, and if the dimension was equal to 5, it would be r to the power 5. The next example we use is d equals to 5 and sub them into these formulas. Looking at the first formula, we have the volume formula where we get 8 pi squared by 15, and for the surface area, we get 8 pi squared by 3. By considering these two, we can clearly tell that if we differentiate the volume on the right, if r was to power 5, we get same value for a. This shows that a equals to dv over dr, which proves that the relation of high dimensions holds there. It is also important to consider that as d goes to infinity, the volume of unit square also goes to 0. Thank you.
Well done, guys. Thank you. Well done. Cash, I'm sorry to be stern with you, but that was worthwhile, and it's an important moment in the progress of your career. Okay.